Okay, and then we'll actually, look at the curve that goes through 0, minus 3 halves. Okay. So let's just put our x, y axes over here. Okay. Here's x, here's y. Okay. Now this thing actually has an infinite number of equilibrium solutions, right? What are the equilibrium solutions? Do that first. Yeah. Stationary points or equilibrium solutions. Stationary points. Well, it's dy dx is a function of y only. You just set the right-hand side equal to 0, sine y equals 0. So you get y equals 0, plus or minus pi, plus or minus 2 pi, right? Okay? Now, suppose I'm interested in that solution. I think it went through 0, minus 3 halves. Remember, we had y of 0 was minus 3 halves, which is minus 1.5. So basically, if I just go to 0 plus or minus pi, I'm okay. Okay? So let's just draw, not all the equilibriums, let's just draw 3 of them. Okay, we've got y equal to 0, that's an equilibrium, so I'll put that a little red line through there, right? We've got another one at y equal pi, right? Y equals pi. And we've got another one, of course, at y equals negative pi. Okay. And all I'm going to do is basically draw the equilibrium between pi and minus pi, okay? Because if I go to above pi, I really can't extrapolate from that. I got to draw y equals 2 pi, right? Okay? So we're just going to look at the equilibrium solutions between pi and minus pi. Okay. So, actually we're going to have basically here. Okay. Let's go over here now, and let's assume I'm in the region over here between these two equilibrium solutions. Okay? I'm between y equals 0, which is an equilibrium solution, y equals pi. Okay. What's the slope? Well, the slope is dy dx equals sine y. What's the sign of a number between 0 and pi? It's a positive number. That's all you have to know, right? So you have a positive slope over here. Okay? And of course, the magnitude of how big that slope is depends where the initial condition is. Is it at 0 pi over 2, or is it 0 pi minus epsilon? Then it's going to be, bigger, right? Because the sign increases. But the important thing is that between y equals 0 and y equals pi, we know that the sign function is positive. Okay? So it has a positive slope for any point that I choose between y equals 0 and y equals pi. That dot can be anywhere between here and here. It has a positive slope. Okay? Has a positive slope, what has to happen? As we go to the right, increases, increases, increases. Can't cross the equilibrium solution. Got to stay in the strip, right? Similarly, as we go from right to left, since the slope is positive, the function is going to be decreasing. So it decreases, decreases, decreases. Can't go into that. Can't touch that red curve because that's an equilibrium solution. Okay? That's pretty good. Okay? Now, let's do the y equals minus pi. Okay? Let's take a point like over here. And that would be the 0 minus 3 halves, right? 0 minus 3 halves is in the strip between y equals 0 and y equals minus pi, right? Minus 3.140, sure, okay. What's the sign function between 0 and negative pi? It's negative. So it means when you go from right to left, it decreases, okay? So we go like this, and we can't cross the equilibrium solution at y equals minus pi. Similarly, since we have a negative slope, as we proceed from to the left, the function increases, okay? Increases, 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 but cannot go into the other region. So it looks like that. Okay? So that's the solution that, so that's the region, basically. Okay? This is a point 0 minus 3 halves, let's say. 0 minus 3 halves. Okay? And if I look at that picture, okay, I'm not going to bring it up again, but yeah, believe me, if you look at that picture, people see the picture again? Okay. Okay. Just have to get this whole nonsense started again. Okay. On. Laptop. Okay. Yeah. So we got this kind of curve. We should see that red curve kind of match that. And also you can see that the red curve actually is sandwiched between y equals 0 and y equals minus pi. Okay? And I had the analytical solution someplace, yeah. you can take the limit of this thing as x goes to infinity, okay? And you'll find out that it equals minus pi, and as x goes to minus infinity, you can prove that it goes to 0. By just looking at that analytically. But let's look at the picture, okay?
The vector field only showed one, like 1.5 periods of it, right?
Yeah, exactly. What would happen is that if you wanted to get that picture, I forgot what range we took on y. Okay, we certainly covered minus 3/2. But if you did that, you see this repeating again. Okay, it's periodic, the sine y. So those equilibriums would be a periodic distribution, as we go along plus or minus y. Okay. Is this covering? Oh, no, sorry, it's covering the, it's covering.
We could probably just raise the back, and we could have it.
Okay, okay, I'm sorry. Yeah, you'll just have to, have good memory. Okay, let's. I should have orchestrated this better, right? I forgot where I am now.
In class?
It might have been under MATLAB scripts.
No, was this chapter 1? No. Oh, shoot. Chapter 2.
Diff field?
Direction field, isn't it?
Yeah.
There it is. Okay. So play this game over here, okay? So you see over there, was there?
Just raise it.
Yeah. Okay.
Cool.
Yeah. Okay. Then we'll pull it down. Okay. So basically, here we are, 0 minus 3/2, and our analysis based upon autonomous differential equations said that the curve falls as we go from left to right. It asymptotes to y equals minus pi, and on the top it asymptotes to 0. Look at that red curve. Okay. See? Asymptotes to 0 on the left, decreases, asymptotes to y equals minus pi. Of course, the minus pi is somewhere over here. Okay, so if you're interested basically kind of like in the qualitative behavior of the solution, say for that initial condition, we did this like, I think less than a minute, right? All I did is I plotted y equals 0, y equals minus pi. I found that the slope was negative, and I know exactly that it has to stay in the strip, and I drew that curve. Boom, 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 right? As opposed to solving this analytically. Now, this is a good example. Suppose you went through the labor of doing this analytically, okay? Unless you're smarter than, much brighter than I am, I have no way of telling you without going to a computer that, oh yeah, this is the shape of that curve. It's not like y equals x squared or something like that, right? God knows what this thing looks like, okay? But using the fact that it was autonomous, we're able to actually get that curve, pretty much a shape right on, okay? I think it's pretty cool. So now probably you can appreciate what I said, that, solving these autonomous differential equations, we're not really solving it. What we're doing basically is taking advantage of the fact that dy dx is a function of y only. It's amazing that one little, it seems unremarkable, right? Big deal. Dy is only a function of y. But once you know that, basically, the fact that you can get these equilibrium solutions, okay, and those are the only points where you have 0 slope, it allows you to basically fill in, by hand, what the graph looks like in any region, okay? And similarly, we could have also gotten this character over here, right? That's y greater than 0, okay? And it looks like they go up, and they also kind of asymptote, okay? And all that information, yeah, we did it over here, right? I didn't do this one over here because you'd have to put y equals 2 pi, okay, and then continue on. Okay. Matter of fact, let's just do it for the fun of it, right? Let's say here's y equals 2 pi is over here, right? That's the next equilibrium solution, y equals 2 pi, okay? And now suppose that I took a point between pi and 2 pi. The sign between pi and 2 pi is pi. 2 pi is negative, right? Sign between pi and 2 pi is negative. So it's going to have a negative slope. That means that I decrease, okay? So like this, and something here I've got an increase, okay? So if you took that direction field and you extended it so it went to y equals 7, let's say, you'd see the arrows going like this, showing that curve, okay? Okay. Let me do, I think we'll do a few more examples, okay? We only have 15 minutes. It may spill into the next class, okay? So if we can get this thing done so you can do the homework on it. And actually, we probably can, okay? Once you've seen one example or two examples, you should be able to do the homework, okay? But I'd like to do a few in class, not just one or two, okay? But now, what a lot of people do when they do it on the exam and they do a homework problem like this is, I don't need a whole bunch of curves. Which says basically sketch solution curves. Suppose you have a differential equation, it's autonomous, and the problem says sketch the solution curves. I want something like this. I don't need like another curve over here. We kind of know that, okay? So basically one curve in one region is enough. I think about people that got like, whoa, what's going on? Because they've drawn multiple curves in the same region, okay? It's not wrong, but it's not really necessary. Okay, so the points to that one. Did sign one before I do. Oh, there's one from economics that I have. Okay. Oh, here's one. This is cool. This one is not in the book. Okay. And I thought it was interesting. And we'll be able to finish this one. dy dt is y parentheses 1 minus y squared. And again, you got to get used to different symbols. Okay, it's not dy dx. Okay, but is that autonomous? Yes, because the right-hand side is not a function of the independent variable. It's only a function of the dependent variable. In any application, you'll know what the independent dependent variable is, right? Okay. So let's look at the solution curves. Let's use this theory that we just developed to try to get, I made my mistake over here, it's t versus 1, right? Okay. First thing we need is our equilibrium solutions, right? So, or stationary points. Well, you set the function on the right-hand side to 0. You find basically y is equal to 0 and plus or minus 1. Those are the only points where you have a 0 slope. Okay, so y equals 0. Okay, we'll just put a red line over that to remind us that it's an equilibrium solution. Okay, and then you got y equals 1. Okay. And then I got another equilibrium solution down here, y equals minus 1. And again, remember that y equals, those aren't just lines to indicate regions, they have significance. All the straight lines, y equals 1, y equals 0, y equals minus 1, all three of those are solutions to the differential equation. Okay? Those called stationary points. Okay. Okay, so let's start now. What happens now is that the region in the YT plane is split how many points now? How many regions? 1 region, 2 regions, 3 regions, 4 regions. Big deal, okay? Each region, let's go and just calculate what goes on. Okay, let's take a curve that goes through, say, above y equals 1. Let's suppose our initial point is over there. We're at a dot, right? Okay, where the white dot is, y equals 1. Okay, we know the slope in that region basically is of 1 sign. Okay, you plug in a number bigger than 1, that's positive. 1 minus y squared will be negative. So therefore the slope is negative, so it falls. Okay, so it goes like this, and over here it just grows. Okay, and this kind of is that thing. Okay, so we go like this, and here we just grow. Now, what we can say with certainty is that if you have an initial point that's above y equals 1, then as t goes to infinity, y approaches 1 from above. No question about that. What happens when we go to the left? All we know is that we go to the left, okay, making t more and more negative, the value of the function starts to shoot up. right? It's arbitrarily large, okay? But we don't know, again, what happens here. Maybe there's a vertical asymptote over here. Or perhaps as t goes to minus infinity, y goes to minus infinity, okay? But maybe at t equals -2, there's an asymptote. So there's nothing to the left of t equals -2. Okay, you need further analysis to do that, okay? But at least we know the shape of the curve in that region. Now, let's take a point between these two equilibrium solutions. Again, I'm not going to put it even at the midpoint, something like that. Well, now y is greater than 0 but less than 1. Well, this guy is certainly positive. What happens to the second factor, 1 minus y squared, when y is positive and less than 1? That's going to be positive, right?
Mm-hmm.
Yeah, like a half, right? So it has a positive slope in this strip, okay? Positive slope in that strip, so increases, but we can't cross into the other region. Similarly, if we go to the left, we have to keep decreasing, but there's an equilibrium solution, so we can't go past. So you got that shape between y equals, for initial condition, between y equals 1 and y equals -1. Y equals 0, sorry. Okay, now, what about over here? Suppose my initial point is between 0 and -1. Okay, what's going to happen? Okay, the slope will be negative, right? Because this guy will be negative and that guy will be positive. Okay, so it just falls, right, as we go to the right. So it falls as we go to the right, negative slope. But we can't go into there, and therefore here we have to increase. Okay, so between two equilibrium solutions, there's a lot of information that you have. Okay? See, when we had this one, for example, okay, up here where there was just one equilibrium kind of hugging the curve, we could just say that, yes, t goes to plus infinity, y goes to 0, and we don't know what happens really as you go to negative infinity. When you go to the left, we don't know if y goes to plus infinity as t goes to minus infinity, or if there's a vertical asymptote. But when you're between two equilibrium solutions, you definitely know. Same thing over here, right? There's no problem over here. What happens? If your initial condition happens to be in this region over here, then as t goes to plus infinity, y approaches -1 from above, right? And as you go t go to minus infinity, y approaches 0 from below. Okay? And then we just have one more region.